Hello everyone. In module 2 we introduced the concept of stress. Basically we said in Mech 260 we are dealing with flexible bodies. Let's say if you have a rod and let's assume that it's made out of aluminum or steel, and in real life it is deformable, it's not rigid. And somebody asked us to deform or change the shape of this rod. Basically we said there are three things that we can do. One is that we can apply a tensile load basically and stretch it. Another thing, we can compress it, right? In other words, we are applying an axial load. Either I'm stretching it or I am compressing it. The second thing that I can do, I can twist it. I can apply a torsional load, right? I can apply a torsional load and twist it. And the third one is I try to bend it, either up or down, right? With each of these things that I'm doing, some internal things happen to this rod, right? Which we call it stress. In module 2, we started with the concept of axial or normal stress, right? And we said, okay, if you apply a tension basically or compression, you are introducing a normal stress in each section of this rod. And also we said, because this thing is deformable, when you apply a tension or compression, this rod is going to elongate or compress, right? Let's get back to the mathematical formula that we had, right? In this rod that we have, basically we said that, well, if you apply a load P, basically if you apply load P, let's say you have a rod, the length is L, we said stress, which we show it by sigma, is P over A, right? And A is this basically cross section area of this rod. And also we said introduce strain, which denoted by epsilon, which is the amount that it's deformed divided by the initial length. Also we emphasize that this stress can be positive or negative. The same for these epsilon, it can be positive or negative. So we said we use a positive sign when the load is tension or the stress is tensile stress, and negative when it is compressive. The same if the length increase, epsilon will be positive, otherwise it will be negative. Also we introduce a law which is called Hooke law, and Hooke law says sigma is equal to epsilon multiplied by E. And we said E is a property of a material which is called modulus of elasticity. E is modulus of elasticity. And we can look it up, find E modulus of elasticity for different material. For example, for steel, for aluminum, for copper, this value is different. How people find out this modulus of elasticity? We said there are certain tests that people can do. We call it tensile test. And in this test, the result is a graph basically which is called stress strain graph. Basically it's pretty standard test. On y-axis we have sigma and on x-axis we have epsilon. This basically graph has a linear portion, and then it has a more complicated and non-linear part after this point, which looks like something like that. And we also said that this portion, this linear portion, is called elastic portion. So we call it elastic portion, meaning that if I release the load, this basically rod or this shaft is going to return back, it's going to bounce back or spring back to its original length, and it is called elastic portion. And in Mech 260 we are dealing with loads or with the stresses only in this linear region, and at the top of, like at the end of this linear region, like over here, we call this one sigma y, which is basically sigma yielding, where the material yields, and then after that it moved to another region which is known as plastic region. Like after this region, it is called plastic region, which the formation is permanent, right? So moving on, with the next topic, we are going to have study another property of a material known as Poisson or Poisson ratio. What it is? So this guy, Simon Poisson, like Poisson, family of the guy, not the fish, maybe, I'm guessing, one day he was maybe eating a gummy, right? Not this one, a big gummy. And then he noticed that, well, if he stretch this gummy, it's elongate. That's good. It was discovered by Hook, his friend, right? But he also noticed when this thing is elongate, at the same time it becomes thinner. And when he apply like a compression load, compress it, it become shorter, but the thickness increase. So we said, wait a minute, maybe beside the longitudinal stress, longitudinal along the length of this bar, longitudinal strain, maybe also something laterally happens. So he called it a lateral strain. So in other words, let's say if as I showed here in this maybe figure or schematic, when the original shape was, let's say, this big dot or thick dot shape, when you apply the load, and this maybe rod, it's elongate, but we see it becomes thinner, right? So we call this direction, when we apply the load, the axial load, let's call it longitudinal strain, right? Which we talk about it. And but also we notice that these things is gonna have also on this two other side some sort of deformation. We call them lateral, basically, strain. And this guy Poisson found that there is a relation between lateral strain, so lateral strain, and longitudinal strain. This longitudinal strain, we know that it has a formula, epsilon delta divided by L, right? Poisson found that there is a relation between longitudinal and lateral, and that relation is a coefficient which denoted by this letter, Greek letter nu. Okay, we pronounce it nu, right? And it is more like a V, but it's more like a curvy shape V. Okay, this nu is called Poisson ratio. And it depends on the property of a material. For example, for some material such as a steel, and this nu might be a number like 0.29, and For example, for aluminum, this nu is 0.33. It's bigger. The bigger this number is, it means laterally it's going to deform more, right? So this is for a steel, and this is for aluminum. This is just for one type of steel or aluminum. You can again Google this number. All this number has been tabulated. If you need Poisson ratio of a specific material, then you just need to Google it. For example, for now you can stop the video and Google the Poisson ratio of aluminum, steel, copper, bronze, and few other materials to find out their range. But you will find out that this nu, the range is between 0, so it's a positive number, and also it is less than 0.5. So most of common material, their Poisson ratio is less than 0.5. Maybe there are some special cases which Poisson ratio becomes bigger, but it's very rare. And most of engineering materials, this Poisson ratio is a positive number, and it is less than 0.5. Also, one important thing that we need to notice is if we pay close attention, we see that this lateral strain and these longitudinal strain, they are opposite in sign. What do I mean by that, right? Let's go back to that gummy things again, right? If you stretch this gummy or whatever, right, definitely it's gonna shrink down laterally. It's gonna become narrower, thinner, right? If you compress it, the length is gonna become shorter, but it's become thicker, right? So in other words, if the length increase, the diameter decrease. If the length decrease, the diameter becomes bigger, right? So in other words, we need to put a negative sign here. Okay, let me put a negative sign here to remind ourselves that this longitudinal and lateral strain, they are in sort of behaving in an opposite direction. Not beside the direction, I mean in sign, the opposite sign. Okay, let's move on to the next topic. Thermal stress. What is thermal stress? So far we know that if you apply an external load to something, like again to this bar, if you apply external load, stress will happen. But also we should keep in mind that stress may comes from heat. How? Let's look at a very simple example. Let's say you have a rod, the same rod that I showed you, and you basically increase the temperature. Let's say you increase the temperature by delta T. Okay, so you increase temperature by delta T. Okay, so you learn in physics that the length of this bar is going to increase, and let me exaggerate. Let's say the length of this bar increase this amount, and you have this formula. Probably you remember it from your physics. If you forget that this increase or this expansion is equal to L alpha delta T, which L is the initial length, and this alpha, again, if you forget in from your physics, we call it the coefficient of expansion, or expansion coefficient. Expansion coefficient, which again for different material, this is a constant. You can look it up and you can find it. It's a very small number, but it differs for different material. All right. So this is a case when this rod is free. The two ends of it is free, so it can extend to whatever length that it wants, or it can basically contract and shrink back to if we decrease the temperature. What if I fix this basically rod between two walls, similar to this shape that you can see, right? I fix it between two walls. Now what will happen if I increase the temperature, right? So increase temperature by delta T. So we'll say, well, wait, if you increase the temperature, still this rod wants to extend, right? Still it wants to extend by L alpha delta T. Then we have this wall, we don't let it to extend. Then it means it's going to be under pressure. We are interested to find that pressure, right? How can we solve it? All right, the way that I do it, I say, well, let's for a moment, let's imagine that this rod is free in one side. Okay, let's say this rod is free in one side. Okay, and let's say I have the wall still there, but it's free from here. Okay, assume it is free at one end. All right, so if we make such an assumption, then we know that because of this increasing temperature, this length likes to increase. How much? We have a formula for that, L alpha delta T, right? Which this alpha depends on the property of the material, or whatever the material it is, right? So this is the amount that the length is going to increase, but we know that this wall is not going to sit there and let it happens. So this wall is going to apply a load, right? It says, hey, sorry, it's going to say, hey, I'm not going to let you go anywhere. I'm going to apply a big load. Let's call that load F, and I'm going to return you back. But what is the power of this force? This force, we learned that can create a delta, which is FLAE. All right, we just learned it in first part of this course, this module. So since we have the wall, this L alpha delta T is being cancelled by this delta. All right, so if I then write down over here that L alpha delta T must be cancelled out by FLAE, otherwise it doesn't make sense, right? Here we have a rigid wall, we have a fixed wall, and there shouldn't be any expansion here. This L alpha T must be gone by something, by this force F. So if I simplify that one, I can find F, which is L E alpha delta T. Or I have also I can also get rid of L, so it's going to be A E alpha delta T. In other words, when I have two walls here, when I increase the temperature, it's going to be a compression, a compressive load in this rod, which is AE alpha delta T. Okay, and we are interested in knowing the stress, sigma. Sigma has a formula, which is F divided by A, and from here I can find out sigma, which is E alpha delta T. We just put a T over here to remind ourselves that this is a stress coming from temperature. Okay, and this thermal stress depends on E modulo of elasticity. It depends on E modulo of elasticity. It depends on alpha thermal expansion. Okay, so next time, remember, the stress is not coming only from a force. It may be coming from increasing temperature. So let's move on to the next topic, which is called shearing stress. It's a different type of stress. Okay, So to demonstrate it, imagine that you are, let's say, you have two pieces, like these two pieces, and you want to glue them together, okay? Or let's say you have maybe these two pieces, different material, right? Wood and a rubber is something, and you want to basically attach them together, okay? So if you attach these two together, what will happen? Okay, let's say these two pieces, and I want to glue them together, right? I want to basically put together these two like that one, right? And let's say I'm allowed to glue them on this area that I make it red, right? Let's say I'm applying, just for a demo, some glue over here. Okay, let's say I put glue all over the place on this one. All right, not a strong glue, but just for a demo. And I attach these two together and I press them against each other. Okay, so now these two has been glued together. All right, and now in this scenario, imagine that I want to separate them. So one way is to separate them, like apply a load like that, right? Try to separate them, which is difficult now because they have been glued together. I cannot separate them. But also imagine that I use this design in something that the load's been applied like in a tensile mode. I'm trying to extend these two. In other words, let's say that I'm applying a load, one over here, F, and another load over there, F, right? So if I try to do so, if I try to apply this load, now these two surfaces wants to slide on top of each other, right? If I try to slide them on top of each other, it's going to be a friction between these two. That friction, or the between these two, is called shearing stress. Let's go back to our math formula. All right, over here. So let's say I'm applying the load as I showed you in that demo, or the same things here in the 2D form, F, and here I have the load F. Okay, and as I said, there is going to be shearing stress. How we calculate the, so between these two layers, imagine if they have been glued together, right? There will be a stress on the glue, which is called shearing stress. We use the term shearing stress to distinguish this one from the basically the normal stress, right? The normal stress is a different type of stress. Okay, just for just one time to have it in your mind, imagine that I have like my two hands, I glue them together. Imagine I apply glue and I attach them together. Okay, I'm not gonna do that, but imagine if I do that. Now if I try to separate my hand, right, that way, that type of stress is called normal stress, because it is normal to the plane that we are interested to find the stress. Okay, that's normal stress. Now the same scenario with my hand, imagine that I try to slide them on top of each other, okay, like that one. That type of stress, which is more like a friction, okay, that type of stress is called shearing stress. That's something that we need to distinguish. How we calculate shearing stress? We say shearing stress is equal to the force that we are applying here divided by A. As you can see, the same formula. But what is A here? A is the area that we glue these two pieces together. In other words, if I go back to my demo that I just showed you, all right, so in this demo, when I glue these two together, okay, if I try to separate them, all right, this area that has been red, this is the area that basically we consider for when we calculate shearing stress. So if I have this length, let's say A, and let's say if I have this length B, then A multiplied by B would be the area which I use in calculating the shearing stress. All right, let's go back to our formula. So F divided by A, and A is the area which we glue these two together, area of applying glue. All right, so let's formulate it mathematically. The same concept, we have over here two plates. I exaggerate the glue here, it's very thick glue, but this is just for exaggeration, okay? And let's say if I have a little maybe a square shape here, which I magnify it over there, all right? So shearing stress, as I explained, it is going to be on the surface. Basically the shearing stress will happening on these layers, right, or bottom or top layers when we apply the glue. We show shearing stress by the word tau, again to distinguish it from sigma, so we show it by tau, and this tau is F divided by A. So that's the formula for shearing stress. And one more thing that we need to know. So this cube, or sorry, this square that I draw here, when I magnify it over here, if I apply this shearing stress, let's say on one side of it, it's gonna become oblique, right? It's gonna skew to a form. It's more like, imagine when when you have a textbook and you try to apply load. Maybe let's say if I have this thick textbook and I apply maybe a load, or maybe if I show a better example for you, this, let me bring one of my book and maybe I draw something on it. Okay, now let's go there. Okay, let's say this is a book, and on this book, it's a thick book, maybe I should start reading it. So I draw just basically a square on it. Now if I apply a load like that one to my hands, imagine that's the glue, right? If I apply a load like that, like this, my left hand try to go to the right and my right hand to the left, right? You see this square becomes skewed and deform, right? And now I'm gonna have an angle over there. So this deformation, let's go back to our formula. This deformation is called shearing strain, right? So shearing strain. In other words, this angle gamma, okay, on the textbook, the shape that I just showed you, this angle of deformation. So how we can calculate that? We need a formula for that. Let's see. Again, this Mr. Hook help us with that. How? Remember we had a formula for, we call it Hooke's law. At the beginning I reviewed that one. So for axial law, so Hooke's law for axial load. Remember it was something like epsilon or sigma is equal to epsilon E, right? So recall we had this formula. So this Mr. Hooke also provided for us another formula for shearing stress. Okay, so Hooke's law for this time shearing stress. Maybe here instead of load I'd better put stress. And this formula goes something like tau shearing stress is equal to gamma, right? We know each of these terms, right? They are new, this one and this one. We know this one is shearing stress and this one is shearing strain, which is an angle, right, which we define it. If I go back, shearing strain is this gamma over here multiplied by a number which is called G. Oh, now we have a new parameters here. So again, recall this E, we call this E modulus of elasticity. Modulus of elasticity. This G also has a name. It is called shearing modulus of elasticity. Okay, and it is again another property of the material, but you may say, well, where I can find it, you say with E we know you will do a tensile test for each material and you can find it. What about G? Do I need to do a tensile test? The answer is no. This Hooke also made our life easier and he gave us a nice formula. I said this G is equal to E divided by 2 1 plus nu, right? So if you do a test and you know E, modulus of elasticity for a material, also there are methods to do a test and find Poisson ratio. This Poisson ratio for each material has been tabulated. Then you don't need to do a test for G. You can just use this formula to find a G. And again, the proof for this formula, you can find it in textbooks, but for this course you don't need to know the proof where this formula basically comes from. It's a little bit complicated, but the proofs are available, and maybe in future if you are interested you can study them more. And let's move on to the last topics of these the last topic of this module, which is basically bolt and rivet or pins connection. Okay, what is this topic about? Okay, remember we said we want to basically attach two pieces together, like this piece and this piece. We glue them together. That's one way to attach them. Another way to attach them is to drill them, and then we use basically a bolts and nuts, or we just use rivets or pins, right? But rivets and bolts and nuts is a common way. So if I bolt these two together, now if I apply load, like a tension load like that, in case of the glue, you saw that when you glue this together, when you apply a load, there is going to be a shearing stress on the glue, right? And that shearing stress on the glue, you could calculate it. But what about when we have like these bolts? This is the purpose of this topic that we want to study, okay? Which this shows basically clearly illustrated. Let's say I have two plates and I apply load F to these two plates. So basically this force F wants to stretch and this portion of the bolt to the right, and this one wants to move it to the left. And as a result, you can imagine that there is going to be basically a shearing stress on a layer on this basically bolt, right? In other words, if I separate them, this load F and F, they want to cut this bolt on this section EE, right? They want to cut it. And this image shows like the upper half, and this one shows the lower half, which you can see this load F create a stress, which this time the type of stress is, since again anytime we want to slide two layers on top of each other, the type of stress is called shearing stress. And this shearing stress, again, if I want to formulate it, tau, this shearing stress is equal to F divided by A. But what is A this time? A is this area, or the area of the bolt, right? Let me again show you a quick image so it becomes more clear. Okay, let's see. I have two plates like that, and let's say I use a bolt, okay, like that one. I can take the bolt out, not that way, right? Let me show you. I take this guy, the nut, and then the bolt. They should not move together, but anyway, you accept it, and something like that, okay? So you see I have these holes here in these plates, all right? So then what I did, I used these basically bolts and bolt these two together, all right? Now if I remove basically the top part of this plate, right? In other words, if I say let's remove the bolts for now, or we can keep them, that's fine, but let's remove this plate. So this is what basically we can see. But let's say in this plate create a section, right? This is the area which we see is going to be under tension, basically under the shearing stress, all right? The area of the bolts, if you apply the load, it's going to cut off through that area. And with a similar concept for the pin or for the rivet, okay, this is called rivet, and that's the same basically concept. This time we use like a male and female portion of the rivet, and they attach together. But in case of a bolt and nut, we use a bolt and nut to tight things together, okay? But the calculation is the same. We're going to have a shearing stress over this area, and again we use the same formula to calculate shearing stress. You just need to be careful that this A here, this A is basically the area of the bolt. You may say, what if instead of one bolt, I have several bolts or rivets, okay, like this scenario that I have here? That's basically the same concept, right? Like here, if I apply a load, maybe this load F, all right, these two layers wants to separate from each other. Let's move back to that one, like here, right? So you see, if I remove maybe this upper half of plate, I have these 3 rivets, right? If I remove them, so I have a plate with 3 holes. That's the first plate, and this is the second plate on top of each other, right? You see from the side. So I have basically I have these 3 plates. Now I put the rivet back there, right? If I remove the plate, you can see the rivet. This is the 3 rivets. So let's have them back together. Now when I apply the loads, this one of these plate want to cut off these basically rivets, and this is where the cutting is going to happen, and over this area the rivets are going to experience shearing stress. How we can calculate that shearing stress? Again, very simple. Shearing stress would be F divided by A, but remember this time A is the total area, right? A is the total area. Or if all the rivets have the same size, so this is then A total. If all the rivets have the same size, then sigma would be, we say this F is going to be divided to 3 because we have 3 rivets, and we can assume that this load being distributed equally between these 3 rivets divided by A. All right, so let's solve a couple of problems to review the formula that we just saw. Example number 1, it's asking us to find the deformation in this rod. So we have a rod, it's not a uniform rod, it's somewhere there is a step, the diameter changed from 4 millimeters to 2 millimeters. We apply a load of 100 Newton, and the rod is made out of steel, and the question gave us module of elasticity. All right, so let's say the formula that we have for deformation, we want to find delta, and we know delta has a formula. The formula is FLAE. All right, so first things that you need to be careful is about the unit. Always I suggest look at this unit for module of elasticity. It is in megapascal. Megapascal means for us Newton per millimeter squared, right? So again, it's not a principle, but as a general rule to follow, it's a good idea when we have megapascal to keep all the units in millimeters, right? Or we can convert everything to meter, but it's better to keep this guy in megapascal and convert all other sizes or other length to millimeters. So the next thing that you need to know is you cannot use like this formula directly just once for the whole things. Why? Because what is this A? Area. You see the area for this portion is something, for this portion of the rod is another thing, right? So then it means I have to break it down. How I can do that is very simple. Simply I say that this rod, I can break it down to 2 sections, from the top to this step here, and then from this step to over here. And then I say myself, well, I call this portion 1 and I call this portion 2. And I say first I calculate delta 1, then I calculate delta 2, and I say total delta is equal to delta 1 plus delta 2. All right, this is the way that I do it. So, but let's calculate each of these. What is delta 1? So it must be F1, L1, A1, and E1. Let's substitute these numbers together. So A1, the area of 1 is pi multiplied by r squared, which is 2 squared, right? And the radius here is, pay attention, it's 2 millimeters. And E1 material is 2 10 to the power of 5. Please pay attention, I kept all the units in millimeters, right? So then I'm comfortable to use E with the same unit, megapascal. And what is the length? It's in millimeter, it's going to be 150 millimeters. It's 15 centimeters, 150 millimeters. What is F1? In other words, what is the internal load here? Okay, that's the question. What is the internal load for this one? If I'm applying a load of 100 Newton over here, it's obvious that this portion 1 is under stretch with 100 Newton, right? Because we can think this portion of 2 as just the medium over there. This 100 Newton is going to be transferred to this portion, so it is 100. And I'll do the same calculation for delta 2. Delta 2 is F2, L2, A2, and E2. Let's put the numbers there. Pi r squared, E 10 to the power of 5. Okay, that's E. Just E1 and E2, they are the same. The whole things, this portion of 1 and 2 made out of same material. L, length of is 20 centimeters, so it's going to be 200 millimeters. And what is F2? What is, if I do a section for 2, what is F2? Well, it is again, it's going to be 100 Newton, because over here we are applying 100 Newton. So if I substitute all these numbers and calculate delta total, it gives me, let me use my calculator. If I do so, delta is 0.358, and I can round it up to 0.36 millimeters. So as you can see, it's a very, very small number, so it's better to keep these 2 decimal points here, but I round it like this 8 and I add 1 number here. So this is then the total elongation of the whole rod. Again, as you see, this number is very, very small, but in Mech 260 we assume that everything is deformable, right, like reality, and we need to calculate this deformation. In some application, maybe even this small deformation is significant. And also pay attention then here that here we have only a small load, 100 Newton. If the load increase, then that's going to be a different story. All right, let's move on to the second example, which is example 2. The same setup, but in this example intentionally I use other units like the US units, so you get used to those type of units. And also in this example the material is different. Like this portion is copper, and this portion is aluminum. Aluminium, right? So 2 different materials, but we have the module of elasticity, and again the same things. We want to know how much the whole things elongate or compress. And another thing that we need to pay attention at the bottom end, we have 20,000 pound force. Remember, that's another unit that in people use. So it's weird. Kips, it's called kips, but it means 20,000 pound. Okay, and something that you need to be careful, we have 140 kips here and another one, we have 40 kips here and we have 40 kips on the other side of this one, right? A total of 80 kips, which this load try to compress this aluminum. These 20,000, these 20 kips try to stretch both the copper and aluminum down, right? But these 40 try to compress this aluminum portion. You need to be careful about the direction as well here. Similar to what we did in example 1, we say, okay, we know the formula, but we cannot use it in one shot. We need to break it down to 2 portions. Let's do that. In portion 1, let's call this one, or because they have a name, we can call them delta of aluminum is, we know the formula, FLAE. So let's substitute these numbers. So A, area, pi r squared, right? The diameter is 3 inches, so the radius 1.5. And speaking of the units, remember PSI. PSI means pound per inch squared. So when I see PSI, I'd better to have all the unit, the length unit in inches. And again, sometimes in textbook they show unit by inch, or sometimes they just show it by this symbol, right? So both of them, it means inches. So E modulo of elasticity for aluminum, it is 18 10 to power of 6. So far good. The length is 40, right, for aluminum. But this F, that's the critical point. That's where we need to be careful and we don't make a mistake here. We need to find out what is this F. It's not difficult, we just need to pay attention. So let's say you don't have these 40 and 40. Let's for a moment imagine we don't have these 40 and 40. If we don't have these 40 and 40, right, then we know because of these 20 that I have, there is a stretch over here. Okay, so I'm just writing it down here. So because it's a stretch, it's a positive load, right? 20. It's coming down. So it's 20. Then I have these 40 and 40, which is a compressive load, right? Try to compress this aluminum up. So since it's a compressive load, and we agreed that compression, we show it by a negative sign, it's going to be minus 80, right? 40 plus 40, I have 80. So it means total minus 60. The load that this thing is experiencing is minus 60,000. Remember, it is in kips, kilopound. We convert it to pound. So I'll do the same for the copper portion, right? Delta cop, same formula, FLAE, and it's equal to, A is easy, pi r squared. E, we have E for copper, which is 15 10 to power of 6. L, the length is 30 inches. That's easy, but what about the force? So we see this copper portion, there is only a 20,000 pound coming down, right? This 40, as you can see, hasn't been applied to this copper. It applied to this aluminum portion, and it is positive, right? It is tension. So here then I have 20,000. If I do my calculation for aluminum, it is, and let's say if I round it up, it's gonna be, let me use my calculator. So it's a very small number, it is something minus 1.886 multiply 10 to the power of minus 5 inches. Let me write down everything's down there so you don't confuse later when you study this. Delta aluminum will be minus 1.886 multiply 10 to the power of minus 5 inch. And if we calculate copper, it is a bigger number, 0.13 inches. Okay, we calculate the deformation for aluminum and for the copper, and if you are interested to find the total deformation, it's gonna be we add just these two numbers together, right? So let's solve the last example, example 3. We have over here maybe a wooden lumber or wall or something, so wooden wall, and then we have this plate, maybe this plate made out of steel, and then we use 3 bolts basically to attach this plate to the wall, and then we apply this 110 kilonewton load. Okay, the question is asking us to find the stress in the bolt. Well, we just learned the formula for calculating stress in the bolt, and we learned that it's not sigma, it's tau. Stress in bolt is shearing stress, which we just explained it a few minutes ago, right? And this tau is equal to F over A. That's the formula we know, right? So tau then is equal to well, because the question says that you can assume that the basically the load is being distributed equally, or it should explain, but we can assume that the load being distributed equally, then it's safe for me, as I explained during the lecture, to say that this 110,000 Newton, I can divide it by 3, and because I have 3 bolts here, and pi radius squared. If I use the calculation for this one, I'm gonna get 1.3, and remember the unit here is Newton, the unit here is basically millimeter square, right? I'm gonna get 1,300 megapascal, right? But let me quickly check that one with my calculator to make sure we get it the right number. So we have 110,000 divided by 3 divided by roughly it gives us and to be exact, let me write down the exact numbers. It's gonna be 1296.8 megapascal, which we can round it up, or we can keep this number as it is basically.